You suggested it, and now it's here. January 15, 2019, Physics Paper 2. We're going to start with question 1. And it's not as hard as many of you might think. Well, if you know to graph, it's not going to be that hard. And all you had to do really was to follow the instructions. So let's get started. Yay. So it says a group of students investigated the relationship between the electric power produced and the flow rate of water, which is channeled through a turbine. Table 1 shows recorded results of electric power, which has units of watts, and the flow rate, which has units of cubic centimeters per second. And here we have the two sets of results obtained from the lab. And then they have here another column that you have to fill out. And 1A says, calculate the cube of the flow rate readings F cubed rounded to 2 decimal places to complete table 1. So we have to see that this is saying F cubed, this is the cube. So whatever is F, this is F. All of these numbers in here are supposed to be multiplied by themselves 3 times, right? And you need to put them to 2 decimal places, and they indicated that here by putting this first number here with the 2 decimal places. So everything you do, you have to do it to 2 decimal places. So it's pretty simple, and we only need the flow rate column. So I hope you can see, maybe not. So we're going to say 0.27 raise it up to 3, and we're going to put that to 2 decimal places. 0.02, because this is higher than, it's 5 and up, so it's going to bump up that to 2. Now 0.34 raised to 3, and we're going to have this at 0.0, and this raises up 3 to 4. 0.04, and then we're going to have 0.39 raised to 3, so it'll be 0.0, you guessed it, 6. Okay, and you keep going, and pretty much once you finish putting in, once you do all the calculations, you get 0.08, 0.10, and then 0.12. Each of these are 2 decimal places. 1, 2, 1, 2, 1, 2, go right down. So question 1A is complete. Then it says on page 5, plot a graph of electric power in volts versus flow rate cubed, right? So here I have the graph paper, and it already has the axis lined out for us. So here we go. So I know that this axis is electric power. P has watts, has units of watts. And then this one has the title for it is flow rate. It's cubed. So cubic flow rate, F cubed, and we're going to put Cm cubed, S to the negative 1 cubed. And we look for our best calibration. So it says here a graph of power versus flow rate cubed. So the electric power will be on the y-axis, and the flow rate will be on the x. It's y against x. And so we're going to now do this. We know for the flow rate, for the electric power, we're going from 0 to 77. And we could go up in 5s. We have enough space for 5. So we could say 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. Yeah, you could have stopped at 80, but You stop wherever you want to stop. Just make sure you stop at a number that's higher than 77. So I'm going to put my numbers in. 5.0, 10.0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, and 100. Okay, and see I kept my little decimal places because I want to be in tune with what they have here, and we have our axis labels. So you see that? All right, nice. And then down here now, we know we're going against the cube, the cube of fluoride cube, right? Cubic fluoride. So we know we're going from 0 to 0.12, and we could do it like this. We could go 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, 0.1, 0.11, 0.12, 0.13, 0.14, right? So we keep adding 0.01 each time. So you notice if you're going up in fives each and you're going the same spacing as each space will go up in 5. If you're going in 0.01, you keep adding 0.01 as you go along. Okay? .07, 0.08, 0.09, 0.10, keep adding 0.11, 0.12, 0.13, 0.14, 0.15. You could have stopped here if you wanted to. You could have stopped here, but it doesn't matter. Once, yes, you put your 0. So once you have your scales, you see that? You have your scales. You are pretty set. So when it's 0, when the power is 0, the cubed fluoride is also 0. So we put that there. Don't forget, when the cubic fluoride is 0.02, the electricity is 13. So we have 11, 12, 13. And again, how you find the numbers, the calibrations in here, the little points, you just said big number minus little number divided by the number of spaces. Here is 15 minus 10, give you 5. You have 5 spaces in between here, divide it by 5, you get 1. So each space is 1. So this is 11, 12, 13. Okay? Now when it is 0.04, the electricity is 25.5. So between 25 and 26. When it's 0.06, it's 38.5. So 36, 37, 38.5 in here. Okay? When it's 0.08, it's 51. Is that 0.08? And we're going up to 51. So here. 0.1 is 64. And 0.12 is 77. Great. Now we could find our best fit line, and it looks like it might go through all the points. I'll be close enough to all of them, and we draw our best fit line. Great. Okay, good. All right, so now that you have your best fit line, we'll look at the next question. So we've plotted our graph, great. And now our next question says to calculate the gradient of the graph. See that? Calculate the gradient of the graph. It's not so hard. So what you have to do is find 2 points on the line. And you need to do the average. So you want to get all the points in here. So I will find a point where the lines intersect. Always find a point where this line intersect two lines that crossing. You don't want it to be in between a space. And I'm going to find one. Well, this starts at 0. And you don't want to take a point that you plotted. So since it starts at 0, we're going to just go further up and use something here. And I'm going to label this as my point 1. And this as my point 2. Okay? Now, when it comes to finding the gradient, it's always rise, which is delta y, the difference in delta y coordinates, the difference in y coordinates over delta x, which is difference in x coordinates. And you could either have y1 minus y2 over x1 minus x2, or y2 minus y1 over x2 minus x1. So if you start with the 2 up here, you must start with the 2 down here. I'm going to use this one. So I'm going to do my y1. My y1 looks like it's 81, 82, 83. Right? So I have 83.0 watts. And then my x now comes down to 0.13. That's 0.13 cubic centimeters per second cubed. Right? So you put your units there. And then for here now, my y2 looks like 6. It looks like 6.0 watts. And my x2 looks like 0.01 cubic centimeters per second cube. So using these numbers, now that you have written out your numbers, you could just put them in, substitute in the equation where they're supposed to go. Right? So here we have, what is y1? 83.0 watts. And y2 is 6 watts. And our x1 is 0.13. And since the units here are so long, I could just put them all together. 0.01. And I'm going to put my units out here. Cubic centimeters per second cube. Extend that. And then I'm going to put it all in the calculator. So in the calculator, we're going to have 83 minus 6 divided by 0.13 minus 0.01. And I got 641.7. Okay. All right. So watts per cubic centimeters per second. Per second cube. Okay. So that's what I got. And that's the gradient right there. Okay. And then now, let's make sure 83 minus 6 over 0.13 or minus 0.01. Good. Alright, so that's what we got. And that's what we're going to write there. So, use a graph to estimate the electric power produced if the flow rate F is 0.22 centimeters cubed. So this is like a trick question, because remember this graph is electric power against F cubed. You see that? And they're asking you to look for F. So what we're going to have to do is say F if F is 0.22 centimeters cube per second, then F cubed would be that same number cubed. And we will get 0.010648 centimeter cube second per second, and then we put here cube, right? So we will get that. But remember, in the question before, they only wanted the F cubed at 2 decimal places. So what we're going to do is collect this answer. We're going to record it at 2 decimal places, correct? So this at 2 decimal places, we will have, since there's a 0 behind here, it doesn't affect that. So we're going to say 0.01 cubic centimeters per second cube. That is the answer right there. So we're going to now look at the graph, and we're going to look at where it is 0.01. It's here, right? And at 0.01, if you go across from it, you realize that it's at 6 watts. So we could say that hence electric power at 0.01 centimeter cube per second cube is, when it's extrapolated, you get 6 watts. And that would now give us our 6 max. Our 2 max, sorry. Our 2 max. Okay, good. Now we have this. The next question says, use your result from part D to calculate the electrical current in joules produced in 300 seconds. So you just say, if power is equal to energy over time, and your energy here is in joules, and your time is in seconds, and of course the power is in watts, right? And they're asking for you to calculate energy. You just transpose. Then energy in joules will be equal to power in watts times time in seconds, right? And so we could just put in our numbers. So we have power, which is 6 watts. And just remember, 1 watt is equal to 1 joule per second. So we could take out the watt and put joule per second times the time, the 300 seconds. The seconds cancel out to give us the unit we're looking for. Okay? And that will give us 1800 joules. Because 6 times 3 is 18, and you just put back the zeros. Joules. And that's our answer for that. Then it says, to determine the flow rate, the students use a stopwatch and measuring cylinder. State 2 precautions which the students may have taken to ensure that the flow rate was accurately determined. Well, this is not so hard. First of all, we have to say that multiple trials should have been taken. So we would say here, 1 multiple trials should have been performed to obtain accurate results. 2, the same person should have been timing. Right, so to make it shorter, I would just say 1, multiple trials should have been performed to obtain accurate results. 2, the same person should have been timing the flow rate to maintain consistency of that person's reaction time. And 3, the water collected in the cylinder should have been read below the meniscus. Then it says state the major energy conversion taking place in the turbine. So we first start off with gravitational potential energy. That's the water just before it falls. Then kinetic energy of the falling water and kinetic energy of the spinning generator turbine. So that's the water hitting on the spinning generator. So the water will cause the turbines to spin, right? And then the electrical energy in the generator coil. So these are the major energy conversions taking place, and so you should get 1 mark for that. Great. Right, so that's the end of question 1. And I really do hope that this helps somebody out there in YouTube land, somebody who really was doing this test and they just didn't know how to graph. I'm just here to help. If you would like this, just send me your email and I would send it to you. So don't forget, make sure that when you make a graph, your calibration is even throughout. You can't say 5 and then 20. You could, but then you're going to end up with a weird graph, right? So you want to make your calibrations even. If you start with increments of 5, you have to continue throughout with increments of 5. If you start with increments of 0.01, you just keep adding 0.01 across with equal spacing. So if 0.01 is every 5 spaces, keep adding that across the 5 spaces. Otherwise, you're not going to get the correct graph. I did not write a title for my graph because it was already given. Then here, you pay special attention to the instructions. They told you to cube F. So if this looked like a bunch of confusion up here to you, read the instructions carefully. It says calculate the cube of the flow rate readings. So it's saying the flow rate readings in here, cube them to get these. And then they also told you to round to 2 decimal places to complete the table. This is 2 decimal places. If you are slow on it, if you still don't know how to do your decimal places, please go on YouTube and look it up. There are a lot of videos teaching you decimal places as opposed to sig figs. Okay, then they say go on page 5 to plot the graph, and you had to use column 1 and column 3 to plot your graph, right, which is what we just showed you a while ago. If you're calculating gradient, it's the difference in y divided by the difference in x. Just remember it is, well, no, I can't say it like that. So this is difference in y over difference in x. Basically, it's rise over run, and you go from there. You could either do 1 minus 2, coordinate 1 minus 2 for each of them, or coordinate 2 minus 1. If you start with 2, you have to continue. If you start with 1, you have to do the same thing below. Then you show your calculations, complete with your units. Otherwise, you're not going to get your full points. Then the next question, you just follow the instructions because the instructions help you throughout, and you do what you need to do. And remember to read carefully. They say when it is F, but you know you plotted P you plotted watts versus F, or P versus F. Yeah, that's how they have it on the screen. You plotted P versus F cubed. So you need to find out what F cubed would be, and then you look for it on the graph, okay? And then, if you know your equations where power is equal to energy over time, you just do a simple transposition, and then you find your answer. This is based on your laboratory skills, and these are things you would have written down in your lab book or type written up for your lab. And so this should have come like second nature to you. Okay, so when in doubt, always talk about doing multiple trends to achieve accuracy. Talk about reaction time when it comes to stopwatches, and whenever you come to measuring cylinders, always try to talk about reading under the meniscus and also avoiding parallax. You state the major energy conversion. That's all in your notes, okay? Well, see you around for question 2.